One of the benefits of identifying symmetry and using it to analyze molecules is determining when certain objects and certain functions would be orthogonal to one another. And this is orthogonal in the same sense that we have seen for wave functions. So for example, if we have a pair of wave functions, so phi sub j and phi sub I, and we do the integral of the two of them together here, that looks like this. Then if that integral is equal to 0, we say the two functions are orthogonal to one another. All right, and we'll be able to use symmetry properties to predict in advance when this will happen so that we can basically save ourselves the effort of evaluating an integral that will turn out to be 0. Now there's another sense in which we see orthogonality, and that is when we're looking at two vectors. So for example, if I have the vector u and the vector v, and I take the inner product, the scalar product of these two, that can be written as follows. If I put this in Cartesian coordinates, the three coordinates of u might be ux, uy, and uz. The three coordinates of v would be vx, vy, and vz. And when I take the inner product, that's just saying ux times vx, so these two times each other, plus these two times each other, plus these two times each other. And if the two vectors turn out to be orthogonal to one another, which in this case geometrically means they're perpendicular to each other, then this will equal to 0 also. Now it turns out that this is the way that we can sort of begin to see how symmetry helps us with determining orthogonality. What we're going to do is we're going to assume that the characters that belong to the different irreducible representations of a point group represent, if you will, a long vector of dimensionality h. Okay, h is the number of operations that you'll find in a point group. I've shown you here the point group for D2D with these 8 different operations. Now if we consider these irreducible representations to be 8-dimensional vectors, what I want to show is that they produce a similar result to the one for two orthogonal vectors. So in other words, we could write, for example, a sum over all the different symmetry operations. If I take the character of the ith irreducible representation and multiply that by the character of the jth irreducible representation, that I will get 0 if I and j are not the same. In other words, if I'm doing this for two different irreducible representations. So let's see how that works with D2D. Let's suppose that I want to generate the, basically to test the vectors that correspond to the irreducible representations of A2 and B1. Right? So in other words, I want to take the inner product of these two as though these numbers across here represent their components of a vector. So in this case, I'm summing over all of the different symmetry operations, and the characters I'm going to take for A2 and B1. For example, this one would be 1 times 1, so that would give me 1. This one would be 1 times minus 1, minus 1. 1 times minus 1, minus 1. 1 times 1 is plus 1. And then I can keep going down. Minus 1, minus 1, plus 1, plus 1. And then add them all up. And I'll see I get 1 minus 1 is negative 1, plus 1 is 0, minus 1 is negative 1, negative 2, plus 1 is negative 1, plus 1 is 0. So by simply taking this inner product of these two rows as though they represent the components of vectors, I can generate some understanding that the irreducible representations are themselves orthogonal to one another because they produce a 0 result from doing that. Now, this will happen between any pair, but let me illustrate it once more for B1 and E. Now you'll notice that E has lots of zeros in its irreducible representation, which means that the only pairs I need to worry about are these pairs. So this is going to generate the following. I'll have 1 times 2 plus 1 times negative 2. And I think it's pretty easy to see that this will generate 0 as well. So I'll have two orthogonal representations from, irreducible representations from this as well. Now, it turns out that this is just a special case. It is one of several special cases or subcases of something that we know of as the Great Orthogonality Theorem. And I'm going to give you the mathematical statement of the Great Orthogonality Theorem, but I want to caution you that we're not really going to use this in its full glory, but I want you to see what it looks like. Okay, if I do a sum over all of the symmetry operations, and I look at a pair of irreducible representations, and I'm going to represent one of those irreducible representations with a subscript I, and we're summing over the r's. Now, there's another part of the Great Orthogonality Theorem that includes the possibility that we have matrices in here representing these irreducible representations. So, for example, we know that this is a matrix, a 2 by 2 matrix. So if I have the m and n, the mn element of that matrix, it turns out there's going to be an orthogonality relationship for that as well. All right, so this is one of my irreducible representations. And another irreducible representation, I'll write a similar way, but with a possibly different element of the matrix. And this sum over all the symmetry operations will give the following. I'll get the order of the group divided by the square root of the dimensionality of each of these irreducible representations, and then a series of delta functions. So if they are not the same irreducible representation, I will get 0. If they are not the same row of the matrix that represents that a multidimensional irreducible representation, then I will get 0. If they are not the same column of that. So in other words, these guarantee I need to be talking about a product over the same elements of the matrices that belong to these different irreducible representations. If I have just a one-dimensional representation, then these will automatically have to be 1, 1 in order for this to work out. So this is a very general statement, and it includes as a subset the one that we have demonstrated over here. But I want to stress that this is a very special relationship. It can be proven. It's proven in some degree in Cotton's book, so you may want to look at Cotton pages 78 to 88. He discusses this. Like I said, I'm not going to ask you to prove it, but one of the consequences of this is that means that we can take an irreducible representation, a reducible representation, and write it uniquely as a weighted sum of irreducible representations. So this is very similar to what we have done in writing molecular orbitals as a linear combination of atomic orbitals. Here I'm writing a reducible representation of our symmetry group as a linear combination of irreducible representations. And it turns out that decomposing one of these in terms of these is something that will be very useful for us, but I'm going to cover it in a different video.